Okay, this is physics 1102, spring 2023, the exam 2 review on chapters 18, which is on electric currents, chapter 19, which is again on what you call DC circuits. And these will be circuits in parallel and series, which we talked about in chapter 19. And then chapter 20 is on magnetism. And this will also be on lab 3, which is on Ohm's law and power of bulbs. Lab 4, which is on voltage and current, voltage and currents. Lab 5, which is on resistors and thermistors. And lab 6, which is on magnetic fields. Okay, so those are the labs and chapters for exam 2. So I'll go through each one of those. The chapters here, you already have the labs. These are most labs that we have in any exam. Exam 3 is only based on 2 labs. Exam 4 we have 3 labs, and exam 5 is based on 3 labs. So I'll go through this as far as sections. So start in chapter 18. We have the battery and the concept of voltage, right? We talked about that a little bit in chapter 17 with electric fields and potential difference. All right, then we have again electric current, which again we defined as I is change of current over change of time. Again, this is coulombs per second. Charge is a current. So we had a charge, protons, electrons, but it's electrons that move in current. We have Ohm's law. Which is voltage is current times resistance. Again, this is in volts, this is in amps, and this is in ohms. All right, as far as that's concerned, so that's Ohm's law, which for linear ordinary circuit, it's a linear relationship between these. All right. We get a little bit again on resistivity. Which is R is rho L over A, where that's the resistivity That's the length of a resistor, and that's the cross-sectional area, which makes sense. The longer it is, the more resistance the current has to flow, and the smaller the area, the increased resistance. This is, again, analogy is just like a water pipe, right? Smaller pipe is going to increase the resistance to flow. All right, so that's that part. Electric power, again, power is in units of watts, and that is, power is V times I. Again, it looks like Ohm's law, but it's not. Power is voltage times current, and we talked about the examples with the fact that we have household circuits that are in parallel, and how that power, which you measure in watts, is the voltage is normally 110 for household circuits times the current, each one plus times the current, and we add those together to get the total power consumed. Okay. Again, we talked about power in household circuits, where this is 120 volts. So again, if you have an appliance that's 10 amps, then it's going to be using 1200 watts of power, right? So we have that. Again, the examples related to the fact that household circuits are hooked in parallel, and you add each device and the amount of power, and therefore the current is additive. All right. A little bit on AC current, alternating current. Which for household circuits oscillates with a frequency of 60 hertz. That's what we use for everyday household use, is AC currents. If you look at the video on power from the History Channel video that I've got posted, you see that as compared to DC current, which is a normal battery. So household alternating current is what we use for all household devices. And that is all for chapter 18. Nothing on superconductivity in this exam. Okay, so moving on. All right, chapter 19, DC circuits. All right. This is where we're just going to be doing simple circuits. Again, simple circuit is we have the resistor, a battery, and some sort of ammeter to measure the volt current. So voltage, so again, V is I times R. And then we talked about the resistors in parallel series. All right. Where 1 over R is 1 over R plus 1, plus 1 over R plus 2, plus 1 over R plus 3, and so on. And in series, the resistors add together, as I've talked about already in chapter 19, and so on. All right? So that's if we have a circuit that's all the resistors on parallel, and this is a circuit where they're all in series. Again, when we talk about combinations, such as this circuit for resistors, all right, it's step by step as I went through how to eventually get it to a single resistor. And like in this case. All right. All right, let's see what else we got. Oh, and then since we also cover this, it's covered in the MCAT test, we call it like capacitors. And in this case, that's given by C with the unit of farads, capital F. And when we have, and the symbol for capacitors are just two even parallel lines. So opposite resistors, capacitors in parallel. All right. Will be C is C1 plus C2 plus C3 and so on. While in series, it's 1 over C is 1 over C1 plus 1 over C2 plus 1 over C3 and so on. Okay. And then finally RC circuits. All right, we talked about with the decay constant. So that TRC is a time constant, and the voltage, the current goes as I is I naught e to the minus T over RC. So it's an exponential decay. So, all right. And a little bit of electrical so that part. And then finally, all right, electrical hazards. All right. Get into this, how a little more than 20 volts is hazardous, but it's a current that really kills somebody. And talk about wiring, safe wire, grounded wire, and then slightly different on use of ammeters and voltmeters. In a circuit, again, for an ammeter, you have the ammeter in the circuit. To measure the current, while for voltage is put parallel across the battery or across the resistor. As you measure the voltage across. So that's the easiest thing to measure, you put it across it. While for ammeters, you have to actually open the circuit and put it in there. It's in the lab, lab related to, resistors, might be lab 5. Anyway, that's one of the labs. So that's chapter 19. Okay. And finally, chapter 20. Okay. Magnetic fields. All right. Magnetic field has a north and south pole to it. All right. Unlike electric charge, like a positive charge, there is no such thing, or we haven't discovered one, as a single monopole. So like a north pole by itself. You always have a north and south pole together, so you end up with a dipole field related to it. Electric currents. Produce magnetic fields. Okay. The Earth's magnetic field, units of fields, Earth's magnetic field, we generally are using the Gauss, because the Earth's field is approximately 1/2 Gauss or capital G. But the MKS, the SI unit, is a Tesla, all right, named after Nicholas Tesla, not the car, and that's equal to 10 to the 4th Gauss, all right. All right, then force. So again, if you have a moving charge in a magnetic field, again, we define as it's perpendicular, so this is V, and V is perpendicular to the magnetic field, which is either going in and out. So magnetic field is going this direction, the charge is moving this way. It experiences a force of QVB, as far as that's concerned. Okay, and then the example with the lab, magnetic fields. Again, when you have a field, this is exactly what I have the lab. You have a charge moving in a perpendicular magnetic field. It moves in a circle given by the radius of mv q over b, where m is the mass of the moving charge, v is the speed it's moving, q is the charge of it, and b is the size of the magnetic field. So that's the radius of the circle. That's in the lab that we did. All right. So that's in the lab 6 on magnetic fields. Field around a magnetic wire, around a wire. B field, we use the term B for magnetic field. So magnetic field is mu naught I over 2 pi r, where r mu naught is 4 pi times 10 to the minus 7th. I is a current, and r is a magnetic field. So if you got a current moving out, we have a magnetic field at a distance r away is given by this in units of Tesla. Okay. And the solenoid. So for a solenoid, which we again have in the lab, B is mu naught N I over L, where N is the number of turns in the solenoid, the I is the current, and L is the length of it. And again, this is the field inside the solenoid. So this is a magnetic field which goes like this, as far as that's concerned. Okay, and this is what we call an electromagnet. Okay, and that is, okay, oh, then we got a little bit of mass spectrometry. Mass spectrometer. Last part. Spectrometer. So if we have two ions, let's say the best example is say carbon 14 and carbon 12. They're identical except that the carbon 14 has 2 exoneutrons, but it's the 6 protons that are deflected. And because it's slightly heavier, it'll be deflected a little bit less. So it goes in the one bin, this goes in the other bin, and by having to go through a magnetic field, again, this is how you can separate two chemically identical isotopes. So again, we get this concept of isotopes. You have that with chemistry. So isotopes are chemically the same, but they have different number of neutrons, so they're slightly higher. Okay, and that is it for chapter 20 as far as exam 2 is concerned. Again, it's going to be consisting of about 15 to 20 multiple choice questions and about 5 problems. All right, so have a good day. Email me if you have any questions, and